Today we're going to look at a first order decay problem. This is a slightly more advanced mass balance than we did in the first video. So I've taken a problem from the textbook here. We've got a lake with two inflows. One of them is a stream or a river with no pollutant, and the other is, an outfall from a factory, and it has a pollutant concentration. The flow is much less than the flow from the stream. So the way we're going to do this, we're going to start the same way we did the last one. We're going to start with the water balance because we know that the water going in is equal to the water going out, and that'll let us find Q3. In equals out. Q1 plus Q2 equals Q3. And, Q1 plus Q2, that's 50 plus 5, so Q3 equals 55 cubic meters per second. Now we want to do a mass balance on the pollutant itself. So this pollutant, this is something that degrades with time in a first order decay reaction. This could be something like BOD, biochemical oxygen demand. So we're going to do the same, but it's no longer just in equals out because we have pollutant going in, pollutant going out, but we also have pollutant decaying in the system. So we need to account for that. So we're going to do in equals out plus decay. And so this isn't a formula that you need to memorize. This is just a way you describe what happens, and it allows you to set up your formula. So what we're saying here is that all the pollutant that goes in either flows out or decays within the system. There's nothing else that can happen to this pollutant. So in order to get the mass flow terms, we're going to do Q1 C1, Q2 C2. That'll give us milligrams per second. Equals Q3 C3 plus the decay term. So that'll be K C3 V. And we use C3 here because we're assuming that that the lake is perfectly mixed. We have the assumption in the problem that says well mixed. And what that means is that the moment that a pollutant enters, it is perfectly mixed throughout the lake, so it will have the same concentration in the lake and in the outfall. Now this assumption isn't perfect, but it's a good assumption, and later on we'll learn how to finesse this if it's not quite the case, if it's not perfectly mixed. So let's start subbing in variables. Q1, C1, since C1 is 0, this term is immediately going to go to 0. So 0 plus 5 cubic meters per second times 100 milligrams per liter. Now we're going to need a conversion factor to balance this term out because we need a mass flow rate, so that'll be milligrams per second, mass per time. But meters cubed and liters, these are both volume, and we need to cancel them out. And we know that there are 1,000 liters in 1 cubic meter. So cancel out meters cubed, cancel out liters, we're good. Equals Q3 C3. So Q3 was 55 cubic meters per second. Times C3. We don't know that yet. Plus K is 0.25 per day. Now these units can look a little weird if you're not used to them. But what that just means is that the pollutant will reduce by 25% per day. That is the rate at which it decays. So 0.25 per day times C3 times volume, which is 10 to the power of 7 cubic meters. Great, so now we want to isolate for C3. So let's do this in 2 steps. We're going to factor out C3 on the right-hand side. We'll simplify the units as we go. We won't do any calculations just yet, though. I always try to do the calculations all in one step at the very end just to avoid transposition error. So we got 5 times 100 times 1000 milligrams per second equals, so we're going to factor here. So we take out C3 times 55 cubic meters per second plus 0.25, simplify the units a little bit, 0.25 times 10 to the 7 meters cubed per day. We just combined the d to the -1, which is the same as 1 over d, and the meters cubed. I combined it into one term just to make it a little easy to work with. Before we close that bracket though, so we have two terms inside the brackets. One of them is in units of meters cubed per second, the other is in units of meters cubed per day. We can't add them together like this. And since on the other side of the equation we have milligrams per second, we're going to be able to cancel out the seconds. So instead of converting the meters cubed per second to meters cubed per day, we're going to do it the other way, and we're going to convert meters cubed per day into meters cubed per second. So that one day is 24 hours. 1 hour is 60 minutes. And 1 minute is 60 seconds. So here we can cancel out days, cancel out hours, cancel out minutes. We have meters cubed per second plus meters cubed per second. Our units balance, great. So now we just solve for C3. C3 equals 5 times 100 times 1000 milligrams per second over, it's going to be a big one, 55 meters cubed per second plus 0.25 times 10 to 7 over 24 times 60 times 60 meters cubed per second. So we have meters cubed per second on the bottom, milligrams per second on the top. So this is going to give us, the seconds are going to cancel out. We're going to get units of milligrams per meter cubed. So now we can plug this into our calculator. And we find that C3 is 2928 milligrams per meters cubed. So that was actually the wrong answer. I've had a correction submitted by a viewer of this video. And, this happens. This happens to all of us. Sometimes we just punch it into the calculator wrong. And that, to me, is one of the great benefits of structuring the problem really clearly, showing every step, crossing out the units as I go, because, for one, it allows me to find my mistake really easily. And in this case, the mistake was just that I put the numbers into the calculator wrong. And then, a nice side benefit is that whoever's grading your paper, they also can see that you had everything right up until the last step. And you're not going to get perfect on it, but it's a lot better than, just having the wrong answer and no clear procedure, because then you can't even get part marks. So the correct answer here is 5,957. And the seconds cancel out, so our units are milligrams per meter cubed. Now, milligrams per meter cubed, that's a unit of concentration. It's perfectly valid, but it's a little strange. It gives us an awkwardly big number. And the units in the question, the concentration units, are milligrams per liter. So let's convert it into milligrams per liter. Even though the problem doesn't specify what units it wants it in, it's usually a safe bet to give your answer in the same units as the question. So we know that 1 cubic meter is equal to 1,000 liters. And that gives us 5.96 milligrams per liter. And that's our final answer here. So I just wanted to highlight that this is the steady state concentration that we found. And what that means is that, when the factory has been running for a long time, it reaches a plateau and the concentration doesn't change anymore. This is the level, this is the long-term level that we can expect to see. However, when the factory is just starting up, so maybe it's just starting up because it's being built, or maybe there's just been a change in the process at the factory, or maybe it's a factory that shuts off sometimes for maintenance or for the weekend, who knows. And so in those periods just after starting up, we're going to see a ramping up. The value is not going to immediately reach 5.96 milligrams per liter in the lake. And we call that the transient state. Now, the transient state is something that we can model mathematically. It's more complicated than this, but we can do that. And, well, you know what? I think that'll be the topic of our next video. I really appreciate hearing from viewers like this, like for Self, who submitted this correction. It it makes it clear to me that this is useful to you, and that I'm just not talking to an empty screen. So thank you very much, and make sure to let me know with any comments what you would like to see, what problems you're struggling with right now, and what can help you through your assignments and exams. So good luck studying, and I'll see you next time.